Eduardo Torroja was born in 1899, and he was both an engineering professor and also a designer, a structural engineer. He was one of the best people in Spain to illustrate the relationship between form and structure in reinforced concrete vaults. One of the geometric forms that Torroja used is the hyperboloid. He used this form, for example, for the water tower shown on the screen. You can develop this hyperboloid form, for example, by taking two rings, punch holes through them around the perimeter, tie strings between these two rings, and then twist the rings opposite to one another. In this way, you will get the hyperboloid form. If you take that image of these rings, turn it on its side, and take a slice of that, you get the hyperboloidal sector that forms the shape for the overhang or the horizontal cantilever of the Zarzuela Hippodrome racetracks in Madrid, designed by Eduardo Torroja in 1935. If you look at the span, the size of this horizontal cantilever compared to its thickness, you see how thin that reinforced concrete is compared to the size of the structure. The reason it can hold its own weight up is because of the form. It's not because how thin or thick a structure is. The fact that these structures are so thin and can carry their own weight indicates that it's about the form of the structure. It's not about how thin your structure is or how thick your structure is. If you have the proper form, you really do not need a lot of material to hold its weight and the loads imposed upon the structure. I can demonstrate this concept for you with a simple piece of paper. The single piece of paper can't hold its own weight if I hold it like this. However, if I just give it a little bit of curvature, it can now hold its own weight. It can even hold a few pieces of chocolate, like this. And you could get creative at home and try different examples. For example, you could take the paper and fold it into a fan shape and even attach a cup at the end. It can hold not only its own weight, but the cup. And then you can see, maybe hold a little competition, who can design a horizontal cantilever to hold the most chocolates in that cup. And you'll be surprised to see the incredible amount of load this single piece of paper can hold if you give it the proper shape. The Zarzuela Hippodrome was part of a design competition. You can see on the screen the many entries that were part of that competition, which represents the many different solutions that an engineer can come up with, an engineer and architect team can come up with for the same problem, that is creating a horizontal cantilever to cover the stands. The final design put forward by Torroja and his team is shown on the left and in the image on the right. However, this design was not the initial or the original design proposed by the team. It was an evolution of thought. In the end, the cantilever spanned 42 feet in one direction and 23 feet on the other side. In the middle there, we see a single support. Let's look at this final form. The original design proposed by the team was a bit different than the final design. What you see on the screen is a design that was a little bit more cluttered, had more structure than needed. Torroja recognized that right away. Let's start by looking at the horizontal cantilever. Remember, it was longer on one side, almost twice as long on one side than the other. You can think of this as a seesaw. Most of you as children played on a seesaw in a playground. And you know that if you and your friend weigh the same, maybe you played that game where you tried to balance that plank on the seesaw so that it would stay still and horizontal. That would only work if you weighed the same and the planks were the same length to the left and right of the support. However, if your friend weighed twice as much as you, he would need to sit about halfway up from that center support for you to find that balanced position. If your friend that weighed twice as much as you sat at the tip of the seesaw, so you had the same length from the support to the ends, you would fly up and your friend would be sitting on the ground. And the only way to get this plank to stay horizontal would be to tie a rope from your end down to the ground. In other words, this rope would be able to hold this plank on the seaside horizontal. That is the concept behind this horizontal cantilever of the structure. Because the left side, the 42-foot span, is longer, it weighs more than the 23-foot span on the right side. So there is a tie that needs to be there in place to hold that horizontal cantilever stable. Torroja realized that that tie was also going to support the roof underneath it, and therefore the column that was there initially to support that roof wasn't needed. Next, he noticed the staff gangway that was right beside that massive column in the center holding this horizontal cantilever and other parts of the structure. That column was large enough to be able to cantilever this staff gangway. In other words, that staff gangway did not need its own column, and that column could also be removed. Next, he removed the supports on the bottom of the stands, again noticing that that part of the structure can be cantilevered and that column there was not needed. So you can see with the first revision compared to the original design, already he's cleaning up the structure, meaning he's removing unnecessary elements. In the next iteration, he sculpts the main column. He creates this hinge-like condition at the base and also at the top where it narrows. The column narrows at the top and at the bottom to reduce the amount of bending moments in that column space. He also curves the structure underneath the supports to create a more elegant appearance. And with these iterations, we have the final design, the winning design of the competition, when if you compare it side by side to the original design, you see a significant improvement. Another revision was the shape of the roof of this horizontal cantilever. Originally, it was a conoid roof, a conoid shape, which is the same shape as the schoolhouse roof done by Gaudí. And in this shape, you have a straight edge at the end, at the 42-foot overhang end. Torroja changed the shape to a hyperboloid roof. And what this means is that at the end, you have a scalloped effect instead of a straight edge. The double curvature of this roof makes it very strong. It withstood substantial bombardment during the Spanish Civil War when 26 holes were blown into it. These holes were covered over with concrete and the roof remained intact. I traveled with some students to visit the Hippodrome, and to give you a sense of scale, here you see a student standing next to that tie. From down below, we see the staff gangway and that column supporting the horizontal cantilever. And sitting at the top seat of the stands, again, we see that column which narrows as it approaches that horizontal cantilever. The design for the Hippodrome was intended for a design competition that had a 3-month time limit. Torroja wrote that the whole process just described was a matter of a few minutes, possibly seconds. He reflects on this experience and, generally speaking, the process of design. And when he does this, he asks himself, was this process an imaginative process, or was it logical reasoning based on technical training? In other words, he was asking himself, was this play or was this discipline? This idea of discipline and play of the engineer, that the engineer is bounded by the laws of physics and equilibrium. So there is a discipline there that the engineer must be knowledgeable in. But inside of this discipline, there is room to play. And he answers this question by saying that it's both together, that it's both discipline and play that brought about this evolution of design to the final form. He says, quote, "The imagination alone could not have reached such a design unaided by reason. To me, it seems clear that the imagination can operate successfully only in conjunction with the basic principles of technical creative work." This is one of my favorite quotes explaining this concept of discipline and play. One of my closest colleagues, Ignacio Payasa Forteza, who is a professor at the Universidad Politécnica de Valencia in Spain, has written many research papers on Torroja and his works. I had an opportunity to ask him some questions. Why don't you start by telling us what inspired you to study Torroja?
It is a curious story because when I was a student, everyone was telling me that Torroja, he was a genius, but nobody was explaining me why he was such a big genius. So then I decided to start doing some work and trying to find the original documentation about his work, doing some analysis to discover why he was such a great engineer, so important.
And what did you discover? What made Torroja so special?
To me, a nice thing was to discover that he had many things to see with E.T.
E.T. the extraterrestrial?
Yeah, Spielberg's character. Why? Not only that none of them had too much hair, not only that they all had the same initials, like E.T. and E.T., but when you study in depth the works by Torroja, you see that his ideas were much more advanced than those of the people of their time. So somehow it was like if he was an alien coming from another planet. He was so advanced that it was just amazing.
Can you give us an example of a project that was so advanced and what year, more or less, this was happening?
Of course, it would be a great pleasure. For me, one of the projects that better exemplifies this is the Frontón de Recoletos that he built in Madrid and was destroyed by some bombing produced by the Spanish Civil War. You can see here an image of the roof. You can see that the interior space was amazing, something very special. But it is even more special if you compare it with the shells that were built at that time by the Germans. For example, with the shells built in Budapest or Frankfurt, the market of Frankfurt. So there you see that the dimensions of Torroja's cell were much, had a longer span, a longer dimension in
Longitudinally?
Yeah, in longitude. But it is not only that, it is also that the cross-section of Torroja's cell was completely new. Nobody before had done this kind of shape with two lobes, as you can see here. The other cells were much more conventional. And also, Torroja, he wanted to make a completely ribless surface. So it didn't have any...
A ribless surface?
Yeah. For example, here in the cells of Budapest and the Frankfurt market, you can see some beams that provide the stiffness and support to the cells. And Torroja, in the intersection between the two lobes, he didn't place any beam.
So where the two domes intersect at that V, at that point, there's no rigid beam?
No, there is a kind of beam, but it is embedded in the surface of the cell, so you cannot see it.
Yeah.
It's a completely ribless surface.
And it took a lot of courage to build such a long span and an unusual form, correct? Because this was a time before computers. This was 1930s or something
Yeah,
like
that's
that?
1936. It didn't take not only a lot of courage, it took also a lot of mathematics.
Okay.
So Torroja, he was a great mathematician. He was, in fact, named a member of the Academy of Mathematics of Spain. So he had to solve a very difficult problem with a system with 54 differential equations. So he had two teams that helped him to solve the problem, and he found two different solutions. So at the end, he arrived to the conclusion that the best thing to do was to compare the results of these mathematical models with a reduced scale model built in a lab that you can see in the picture. But the thing is that at that time there was no company in Spain that was able to make these reduced scale models, so he had to create the company. So somehow he became an entrepreneur, because at that time there were no companies in Spain able to build this kind of reduced scale models, and he created a company called Icon to do these models and similar models for other structures.
The cross-section of Recoletos reminds me a little bit of the Romanesque churches.
Well, there are some similarities, like the shape of the arches, but there is a very important difference, is that in the Romanesque churches you always had a column supporting the vaults, and here Torroja, he took the column away.
You mean a column would have been in between the two vaults?
Yeah,
in the
but
Romanesque
here
churches.
Torroja is like a kind of magician that takes away this column and the structure still stands, so this must have been like something completely new for the people of that time. He is like a magician. He does things that nobody can understand how they happen.
You've written many research papers on Eduardo Torroja and his projects. Can you just list a few of those projects that you've researched? And can you tell us, have you found magic, so to speak, in all of them?
Okay. Well, for example, we had done research on the Ayoz Aqueduct, on the St. Nicholas Church in Gandia, on some projects that were not built. And it was very curious to realize that some of these projects that were not built because they were too new and too advanced for the time. So, for example, he did a kind of factory for airplanes, hangar, do we say hangar? a hangar, and it was a completely new shape. It was 20% less expensive than a conventional design, but it was never built. And Torroja, he wrote that it was not built maybe because it was too revolutionary for that time.
So the owners did not have confidence. Is that more or less what happened?
We don't have any clue about that. The only clue that we have is that Torroja wrote that it was 20% less expensive than the conventional design, and that maybe it was not built because it was too revolutionary.
Well, thank you very much for talking to us about Torroja. It was very interesting. Thank you.
It's been a great pleasure. Thank you.
By now, hopefully, you're starting to see that there are many possible solutions to an engineering challenge. Next, let's examine a dome designed by Torroja and compare Torroja's approach to design to that of Nervi.